Welcome to Programming Fluency. This is section 8.1, malloc and free. Every variable and array you have built so far had its size fixed before the program ran. In this video, you will learn how to ask for memory while the program is running, using malloc and free. Let's begin. Welcome back. Every variable and array you have built so far lives on the stack, with a size fixed before the program even runs. But what if you do not know how much data you will need? A text editor cannot limit a file to 100 lines. A web server cannot predict how many connections it will get. In this video, you will learn to ask for memory while the program runs from a region called the heap. The two tools are malloc, which requests memory, and free, which gives it back. This is the plan for this video. First, why the heap? The stack cannot grow on demand and it cannot outlive a function. Next, malloc and free. You request a block of bytes, then return it to the system. Then always check for null. Allocation can fail and you must handle it. After that, memory leaks. Memory you allocate but lose the pointer too. Finally, dangling pointers. Using a pointer after the memory is freed. Let's start with why we need something new. Local variables live on the stack. They are created when a function is called and destroyed when it returns. That is automatic and convenient, but it is also rigid. Stack memory has three limits. Its size is fixed at compile time. Its lifetime is tied to the function call, so it vanishes on return. And the whole stack is only a few megabytes. The heap solves all three. You choose the size when the program runs. You control the lifetime, so the memory stays until you release it. And it is limited only by the whole system's memory, which is gigabytes. The trade-off is that you are responsible for managing it. Let's picture it. Think of the heap as a warehouse full of storage blocks. When you call malloc, the warehouse hands you a receipt. That receipt is a pointer holding the address of your block. When you are done, you call free to return the block to the warehouse. Now the definition. Heap allocation means requesting memory at runtime from the heap using malloc. You pass malloc a number of bytes. It finds a free block of that size and returns a pointer to it, or it returns null if it cannot. The block stays yours until you free it. Unlike stack memory, it is not tied to any function's lifetime. This is the complete pattern and every heap allocation follows it. Step 1. Allocate and check. Malloc of sizeof int asks the system for 4 bytes, enough for one integer, and returns the address into the pointer p. We immediately check whether p is null, and stop if it is. Step 2. Use the memory. We write 42 through the pointer, with $p equals 42, then print it. Step 3. Release. Free of p returns the 4 bytes to the system. The output is value 42. One important warning. Malloc gives you uninitialized memory. It holds whatever bits were already there, so you must write a value before you read it. Allocate, use, free. Learn this rhythm. This figure shows the 3 phases as a flowchart. First we allocate p equals malloc. Then a decision is p null. If yes, allocation failed, so we report an error and return. If no, we go on to use the memory, then free it, and the block becomes available again for a future malloc. Phase 1. Allocate. Malloc returns a pointer or null. Phase 2. Use. You read and write through the pointer. Phase 3. Free. Free of p returns the block to the heap. Watch 2 dangers here. Miss the free step and you leak memory. Use the pointer after free and it dangles. We will meet both bugs shortly. Let's zoom in on the null check because it is not optional. Malloc returns null when it cannot find enough memory, usually because the system is out. If you then dereference that null pointer, your program crashes with a segmentation fault. So you check every single time. In this code, we ask for 1,000 integers, and if data is null, we print an error and return. You might think malloc never fails on your machine. For small allocations on a modern system, that is almost true, but almost never is not never. In a loop with very large blocks, or on an embedded system with little memory, malloc can and will return null. Programs that skip the check crash silently in production. This is the most common use of malloc. Not a single value, but an array whose size you do not know until the program runs. The user enters n at runtime. Then malloc of n times sizeof int reserves n times 4 bytes, enough for n integers, and we check for null as always. The nice part is that the returned pointer behaves just like an array name. You can write scores of I to reach each element, thanks to the pointer array equivalence you learned earlier. Scores of I means star, scores plus I when you are done. One call to free releases the whole block. This is how programs adapt to their input instead of guessing sizes in advance. A quick but important idiom. When you call malloc, always compute the number of bytes with sizeof. Never hardcode a number. The best form is malloc of n times sizeof star data. The second form, sizeof int, is also fine but names the type explicitly. The third form, n times 4, is bad. It hardcodes 4 bytes for an int, which is wrong on systems where int is a different size, and it breaks silently if you change the type. Why is the first form best? Star data means whatever data points to, so sizeof star data is the size of one element. If you later change data from int star to double star, this malloc adjusts itself automatically. Now the first big danger, the memory leak. A memory leak happens when you allocate memory but never free it. In our warehouse picture, it is a lost receipt. The block is still reserved, but you have thrown away the only pointer to it. Look at this function. It allocates data, fills it with squares, and then just returns without calling free. The local pointer data lives on the stack, so it is destroyed when the function returns. But the heap block it pointed to is still allocated, and with no pointer to it, there is no way to ever free it. The figure shows this. The pointer is gone, dashed in gray. The heap block is orphaned, outlined in red, leaked and unreachable. Call this function 10,000 times and you leak 40 megabytes. The fix is simple. Add free of data before the function returns. Now every byte that was allocated is released. The general rule is this. For every malloc, there must be a matching free on every execution path. That last part matters. If a function has early returns for errors or edge cases, each of those return paths must either free the memory itself or hand the pointer back to a caller who becomes responsible for freeing it. In a short program, a leak may not matter because the operating system reclaims everything on exit. But in a long-running program, like a server that runs for weeks, leaks pile up until the machine runs out of memory. Now the second big danger, the dangling pointer. A dangling pointer points to memory that has already been freed. In our warehouse picture, it is a receipt you keep using after you already return the block. Look at the code. We allocate store 42 and then free the pointer p after free. P still holds the old heap address. But that memory has gone back to the system. It may be reused by the next malloc or overwritten by the heap manager. So reading star p is undefined behavior. It might print 42 by luck, might print garbage, or might crash. The figure shows the pointer still aimed at a dead slot, drawn as a red dashed arrow. The value in P did not change. What changed is that the memory no longer belongs to you. So how do you defend against dangling pointers? Use the set to null convention. Immediately after freeing a pointer, set it to null. Now if some code accidentally uses P, it dereferences null and crashes right away. That is actually good news. An immediate clear crash is easy to debug. Compare that to a dangling pointer, which silently reads or writes freed memory and produces bugs that show up far from the real mistake. Setting to null has a second benefit. It protects against a double free, because freeing the same block twice corrupts the heap. Since free of null is guaranteed to do nothing, a second free after setting to null is harmless. This is the payoff of heap memory. Because it is not tied to a stack frame, a function can create it and hand it back to the caller. Look at create array. It allocates n integers on the heap, checks for null, fills them with squares, and returns the pointer. Why not just use a local array, int r of n, and return that? Because a local array lives on the stack. It would be destroyed the moment create array returns, leaving the caller with a dangling pointer. That is exactly the bug you saw with returning the address of a local. Malloc moves the array to the heap, where it survives on its own, independent of any function. There is one contract to remember. The function creates the memory, but the caller now owns it, and the caller must eventually free it. Let's collect the 3 ways a pointer can end up dangling. First, use after free. You free P, then write through it. The pointer is used after its block was returned to the system. Second, returning the address of a local variable. The function returns, its stack frame is destroyed, and the returned pointer aims at reclaimed memory. This is the stack version you met in Chapter 6. Third, double free. You free the same pointer twice. The second free corrupts the heap manager's internal bookkeeping, which can crash a completely unrelated malloc later. The first 2 leave a pointer to freed memory. The third damages the heap itself. Setting pointers to null after freeing defends against the first and the third. Now 2 common bugs. The first, forgetting to multiply by sizeoff. Here the programmer wrote malloc of 100 wanting 100 integers, but malloc takes a byte count, not an element count. It does not know you want integers. So 100 means 100 bytes. With a 4-byte int, that is room for only 25 integers. As soon as you write to element 25 or beyond, you write past the end of the block and corrupt the heap. The fix is the sizeoff idiom. Malloc of 100 times sizeoff star r gives 400 bytes, which is exactly 100 integers. The second common bug, use after free. Here we allocate data, store 42 and free it. Then we read data of 0. The problem is that free returned the memory to the system, but it did not change the pointer. Data still holds the old address. It just does not own that memory anymore. Reading data of 0 is undefined behavior. It might print 42 because the old value lingers, might print garbage because the heap manager reused the space, or might crash, and it can change between runs and compilers. The fix is the set to null convention. After free of data, write data equals null. Now any accidental read of data crashes immediately, which is easy to find and fix. Let's recap. Malloc allocates a block of bytes on the heap and returns a pointer to it. Free returns that block to the system. You control the size, chosen at runtime, and the lifetime until you free it, but that also makes you responsible. First, malloc returns a pointer or null, so always check for null before using it. Compute the byte count with sizeof, and remember the memory starts uninitialized. Every malloc needs a matching free on every path, or you leak memory. Using a pointer after free is a dangling pointer, which is undefined behavior. Set freed pointers to null, and remember that heap memory can outlive the function that created it. Next, malloc gives you one fixed block. In the next section, you will meet calloc, which zeroes memory for you, and realloc, which resizes an existing block, and you will build a dynamic array that grows on demand.